All right, we've got a quantitative buffer preparation question here. So we're asked to, we want to make a buffer that has a pH of 4.5. That's known. And we're told that we know something about like how much of the acid we've added. Okay, and we need to know how much of the conjugate base should be added. And then we're also given the Ka of the acid that we're working with. So pretty quickly, as soon as I see that word buffer and then I'm going to make it, I'm thinking Henderson-Hasselbalch. That's why I've titled this HH up here. So the Henderson-Hasselbalch is pH of a buffer equals the pKa of the weak acid plus the log of the concentration of the conjugate base over the acid. Okay. So in this case, we can solve for this. We know this because we have Ka. So we're going to take the negative log of 1.8 times 10 to the negative fifth. That's 4.74. We know the pH because we're told we want to make a pH of 4.5. And then we know the molarity, the concentration of acetic acid. We're already starting with a 1.25 molar concentration. So we have everything. We just need to solve out what is the CH3COO minus. All right. And just as a reminder, of course, I can't just add in this. I have to add it in as a salt. You can't have an anion sitting with a bunch of other anions. It has to have a cation paired with it. So it's a salt, it's potassium acetate. So when you read that though, remember that this, if it's going to dissolve, which it does, it goes in as K plus and CH3COO minus. This being a group 1 metal that is not very densely charged, doesn't prompt any hydrolysis reactions. In other words, it's not going to make any H plus or OH minus, and so we can ignore it. It's a spectator ion. This, however, obviously is important because it's the other component of our buffer. We need the acid and its conjugate base. That is the conjugate base of acetic acid. All right, so we need to know how much we're going to add to that. Add to our 750 mils, which we'll remind ourselves we need to come back to. We're not just looking for concentration, we need a mole amount. All right, so let's get to our calculation here. So 4.5 equals 4.74 plus the log of CH3COO minus, our unknown, divided by 1.25. All right, so 4.5 minus 4.74 is negative 0.24. And notice our target pH is lower than the pKa of the acid, which must mean that I have more acid than base in this solution. So I'm already going to guess ahead of this that I need to have, I'm going to find a concentration less than 1.25. So I keep on yelling at you about like, hey, do some reality checks. You already can have an expectation for what this number is. It's got to be less than 1.25. So go into your calculator punches with that knowledge so you can avoid making mistakes that otherwise you could catch. Okay, so I'm just going to abbreviate that as X and 1.25. I got to get rid of my log here. So I'm going to raise both sides by 10. So 10 to the negative 0.24 equals X over 1.25. 10 to the negative 0.24 is 0.575. And then I'm going to multiply that by 1.25. Make it clear that that's not my X, and that equals X, which I have left as my CH3COO minus concentration, and that is 0.72 molar. And actually, let me not round so early. Molar of our conjugate base. But at this point, don't stop because you get this wrong. Yes, you just successfully calculated the molarity, but I didn't ask for the molarity. I asked for the number of moles that should be added, okay, of the potassium acetate. And that's going to be 1 to 1 because for every 1 unit of potassium acetate, I have 1. Shouldn't have drawn that there because of course that is neutral. Okay, so let's do that for ourselves now. So 0.719 moles per liter And I'm putting this into, I want to make 750, so that's 0.750 liters. And that's gonna be 0.54 moles of the potassium acetate.